morning, everybody. Just to give a quick summary of what we're going to present today. I'm Justin Birdwell. I work for the U.S. Geological Survey, and I'm the president-elect for APG EMD, which helped organize this event. This is our second installment of the Freeware for Freelancers webinar. I want to thank Kirkwood Oil and Gas and Mike Bingle-Davis for hosting us and allowing us to use their Zoom account. And also want to thank our speakers. That will be Ashley Dowds, who will be talking about Power BI, Daniel Kautz, or is it Kautz or Coots? I should have gotten that during the dry run.
It's Coots, but it doesn't really matter.
Okay. We'll be talking about various digital geology tools that you can use based in R and Python. Christopher Ramalia is going to talk about OpenTech platform and various applications of that tool. And then David Thule is going to tell us about the LAS facies log tool for evaluating rock facies from logs. So in the interest of time, I'll just get going. Hopefully you can all see my screen. And this is the latest and greatest in terms of USGS web presence for data serving to the public. It's been around for a little while, but it's been revamped recently. And just for your information, USGS has recently adjusted our data policy, so there's a greater emphasis on serving data to the public in a useful, machine-readable, multi-platform format. And so Sciencebase is kind of your first stop for that. I'm sure some of you have also used miscellaneous USGS websites, tried to navigate through Pub's Warehouse, things like that, if you've been on the hunt for USGS data. And the hope, and I don't know how far along this is, but my understanding is the goal is to have Sciencebase be the place to go where these kinds of data sets are easy to find. And so in the interest of just a quick demo of what you can do with this, I'm going to search for some data sets that I've published with collaborators recently. Oh, okay, this is the wrong thing. Sorry. Apparently there are a bunch of maps of various things named Birdwell that I was not aware of. Going to data releases. These are, as you can see, various different geochemical and mineralogical data sets that I published as part of my work with the Central Energy Resources Science Center. One that might be of interest to folks is an extensive geochemical data set that I and Kate French published. It's related to an article from Organic Geochemistry from a few years ago. It includes thermally immature Eagle Ford geochemistry mineralogical data from a core we drilled in Waco back in 2015. So this is one resource. There's, again, I'm just showing a few of the data sets that I helped publish, but there's a ton of stuff on here. And I hope you're all able to, navigate it. It's a much better interface than a lot of our previous web options. Some other data resources, and again, you'll get links to all these sites in the document we're going to send around to participants. But this is a sort of a general data resources site from the Columbia Environmental Research Center. So pretty much all the USGS science centers have something like this. So if there's a particular region or subject area that you're interested in finding out, what kind of USGS data is available. If you know your local science center, or if you've collaborated with somebody who has a, particular specialty, and they've generated data, there's a good chance you can find links to that kind of stuff on these science center websites. We also have this science data catalog, which is a way of sorting data that's generated by the different programs and mission areas within the USGS. It's essentially taking the same stuff that's in Sciencebase and organizing it a little bit differently by program. And some of this is for political reasons, so that when staffers ask what we're spending our money on, we can point them to these kinds of things where an entire program's recent work is available. But it's kind of neat. It's got access to the produced waters database, which is going to be updated very soon, I've been told. various data sets related to oil and gas assessments that we've conducted recently. So this is related to the Eagle Ford assessment from 2018 that Kate Whidden conducted. Tons of stuff, again, directly related to energy, various aspects of the energy program. I'm not going to go through that. That's just another data release. One thing that people might be already aware of is there is a fairly extensive geochemistry database available from the Denver Petroleum Geochemistry Research Laboratory. This is a downloadable database. It has around 200,000 entries for rock, oil, gas, and miscellaneous other kinds of data. Again, it's something that needs to be updated, and that is in progress. Not really sure when the version 3.0 is going to roll out, but keep an eye out for that. And then, of course, there's Pub's Warehouse, where if you know of a publication that has a map or a data set that you're interested in, eventually this is going to fully integrate with our ScienceBase interface, and you'll be able to, in theory, find the pub you're interested in, and then that will take you to the data set. I'm not sure how far along that is. Again, you know, a lot of our web presence has been updated fairly recently, but that is one of the things that will hopefully be done in the near future. So with that, I think my time is just about up, and I'm going to hand it off to Ashley, who is going to talk about Power BI.
Okay, thank you, Justin. I hope everybody can see this. So I'm going to be talking about Power BI, and I'm going to go through one of the data sets that the USGS publishes for free. And so Justin gave a great overview. We're just going to be talking about one of those data sets. An introduction to myself: I am the principal geologist at Core to Core Geologic, so it's my own independent consulting company. A quick biography about me: I've been in the oil and gas business for over 20 years, looking at different conventional, non-conventional plays, as well as international offshore plays. I've worked for super majors, utilities, small independents, and government contractor. So I've seen the spectrum of different realms of the energy sphere. And my focus has been on exploration, near-field wildcat development projects that integrate, concepts of geology, geochemistry, sequence stratigraphy, and petrophysics. And I spent several years evaluating and assessing new technologies and their usefulness in the oil field. So, I mean, that's all neat and everything, but I thought it would be nice to have a visual representation of my strengths. I see a lot of people doing, the geologic time scales of the resumes and putting maps on their resumes, but I thought it would be neat to do a word cloud. So you can see, like, these are the strengths that are in my resume. So anything that has a larger font shows up multiple times in my resume. So I have a lot of background in the gas plays, working Marcellus, as well as a lot of the Appalachian Basin stuff, and also being on the potential gas committee. Obviously Marcellus is in there, AAPG is in there a ton because I've presented a lot at AAPG. And then it just kind of gives an overview of my background. So I thought that was a neat representation, kind of a side note, but thought it was a fun way to show that. So on to Power BI. So if you rent or buy a license to Microsoft Office, you have access to the free desktop version of Power BI. You can also get a paid license, which I do not have familiarity with, so I'm not sure the advantages there. Everything I've done is in the free version. And in Microsoft's own words, Power BI is a business analytics service. It aims to provide interactive visualizations and business intelligence capabilities with an interface simple enough for end users to create their own reports and dashboards. And that's exactly what I like about it. So I've used Spotfire for many years, and I find this just so much easier to import data and to make visualizations than Spotfire. So I would, highly recommend that you take advantage of some of the resources that are available through Microsoft and other places. So when you open up Power BI, Microsoft has this splash screen, which I can't really see, but there we go. Okay. And it has access to blogs and forums and tutorials, valuable resources that you can, have some good information about how to use Power BI and some of the secrets maybe to getting the most out of your data set with it. There's also a lot of online learning options. So I took a class from EDX. I took the free version. I did not get the certificate. I took this one, Analyzing and Visualizing Data with Power BI. And it was good enough to just get me going and get me into my data set so I could start learning some things. They also have a professional certificate. I'm sure there's other online schools that do that, but this was a quick and easy one for me. So let's see, gonna move this. There we go. Okay, so again, this is the data set that we're going to be looking at. It's the National Geochemical Database. It's the rock portion of it. And when you go to the USGS's website to download it, if you scroll down, there's a download portion. I took this zip file here, which is all the tab delimited text files. And when you download it, this is what you get. You get all of these tables. That this is a relational database. So essentially everyone has the same primary key, so that, this being the main table that has all your location data, your depth data, all the background information about where the sample came from, and then it's linked to all these different tables. So that's what we're going to be importing. Like I mentioned, there are, I'm using the free version, and I also don't have access to ArcGIS, but they do have an option for it in Power BI. If you had that plugin, you could click on this little visualization here, and I'm sure that there's a ton that you can do in ArcGIS in the free version. I'm limited to 10,000 data points, which is why you see this really nice cutoff line at this latitude right here. So it's only showing me the first 10,000. Now, I'm using the free map that comes with Power BI, and I think it represents exactly what I need. I mean, my coordinate systems are the same, so that's great, but there is a version so that you can just display all of your data. So we'll just walk through bringing some of this data in. So you're going to get data, you'll select text. There are a ton of options of different formats to bring data in. You can see this bar right here and how far it goes down. You should definitely investigate all the options that are available to you. And so when you click on your basically meta table, it comes up and it gives you an overview of the first 200 rows. And just so that you can get a sense for what it looks like, and if you like it, great, you can hit load. But I definitely recommend you do transform data, because there's going to be a lot of intricacies to making sure that you have the right data types in there. It does have some options once you hit transform data, where you can look at the column quality, which will be how many data points Power BI can tell are valid, have errors, or are empty. And then it'll also give you a column distribution, so you can see what representative what your data looks like before you bring it in. Keep in mind, this is only based on the first 1,000 rows. And I think in this particular data set, it's actually 60,000 plus rows. So if you need to pull in more to look at it, you can, but Power BI just wants to give you the first 1,000. And so, okay, and again, it also depends on if it can actually read the type of data that it is. You may have to change that, which is what we're going to talk about next. Before you bring it in, you're going to want to make sure that you that Power BI has identified it correctly. In this particular instance, it has the collection date as a text, and that's because it's reading all these nulls in the first 1,000 columns. You need to change that to an actual date mode. And then once you do that, Power BI also will keep track of all of the changes that you made to the data set before you brought it in. And if you didn't like any change that you did, you can just click on the X and it'll revert back to the previous setup. So that's pretty cool. And then once you're done with that, you hit close and apply. And then you need to do a little bit more cleanup. Sometimes Power BI doesn't always recognize map coordinates, so you actually have to physically tell it which columns represent your coordinates. In this case over here, this is the primary table that we've been working with. In latitude, it should have a little globe symbol right there. If it recognized it, it does not. So you just click over here on latitude, come up to here and select latitude. It'll change it, but you're also going to want to make sure that you hit do not summarize. For a lot of the numeric portions it wants to summarize the data, I'm sure that there's some setting behind the scenes that I can take that out, but I haven't gotten that far yet. And then once you've done that, you want to get your other tables and import all of those. One of the things to keep in mind with this particular data set is that when you look at each one of the lab data that comes in, there's going to be a mix of text and numbers. For example, here's one of the columns from the data sets, and we know that we would expect a number in here because it's going to be in parts per million, but it recognizes it as text because of the nulls. Whoops. So you're going to have to go through and change it to a unique number that represents your null. So in this case, I did -999. Okay, so then once you've done all that, you have all your data sets in, and this is the main page that it brings you to, and we're going to be talking about the filters that you can apply, the different visualizations that you can look at, and then over here, the fields that represent all the different columns and tables that you have in your data. And then last thing before the demo is you can go over to the relational database tab and see how Power BI has identified what the primary key is between all these data sets. And in this case, it recognized immediately that lab ID was the common key. And so it made that connection for me. I didn't have to do anything, but if you wanted to change anything between those data sets, you could do it here. So, okay, here we go. Fingers crossed, live demo. Going to switch over to Power BI. Stop share. Okay. Okay, so this is very similar to the setup that I showed in that flyer that I sent around as far as the different a few different visualizations that you can make in Power BI. I'm just going to quickly show you how fast it is to make a visualization here. So here are all the tables that I imported, the top one being most of the background information that I need about each sample. And what I'm going to do is I'm going to make a map real quick, make it whatever size I want, bring the latitude over to the latitude column, bring in longitude, and then for this data set, I am going to show the copper as the size of the data set. And that's actually going to be the count of. So we can see places where there's a lot more data points in the spreadsheet than others. And so what you can see is that as soon as you make this, this map, Power BI is going to recognize that you can filter on any of the things that you included in the map. So for example, if I want to filter for anything that has greater than 100 data points, I'll just apply that filter and it'll take off the map the ones that don't meet that criteria. So I'm going to take that off. For all of the visuals that you make in Power BI, you can go to the format section and just change a bunch of different things like the data colors, the size of the bubbles, different map controls. You can make a heat map too, and it'll show you, again, data density on the map. But so now You can see how quickly we can make that map. Now I'm going to show you how you can query things on a page. So here again, we're back at those 4 primary visuals as soon as my computer catches up. And so over here, I have the stratigraphy that has been applied to each sample, and I can interactively click, and I just want to see all the null data points. It's going to update all the other graphics on here, and it'll show me, for example, the amount of this particular portion of the pie that represents null values within the database. I'll be able to come over here and change my zoom sliders so that I can have a more representative distribution along my x-axis for the data points there. Let's see, I can also, if I re-click that, it'll bring everything back to the way that it was. And I can add a filter for the entire page, all the visualizations on this page, or I can do it on all the different pages that you create within this, this one kind of dashboard. So in this case, what I'm going to do is I'm going to filter by country. I'm going to come up to my main page, go to country, drop it on filters on all pages. And then I'm going to start typing in for the United States because I'm looking at the ones that have states in there. And it'll update everything over here in just a minute. And so you can see that the map zoomed in and everything has changed on here. So here's another example. We can click on Alaska. It'll zoom in there for us. And then I think this is pretty neat. It'll highlight the portion of the different stratigraphy that are involved in these maps. And again, we can change the zoom slider so you can get a more representative distribution of the data set. So the last thing that I want to highlight in Power BI, that's a pretty cool tool, is something called groups. So you can imagine with such a large data set that we're playing with that sometimes there's going to be some misspellings, or like, for example, in the Green River formation, sometimes it's going to be spelled out with FM period, sometimes actually going to be spelled out formation, and sometimes they're going to include the members. And for my particular purpose, I may not care about the members. I want to have everything lumped together so that I can display all that data together. And so what you're going to want to do is make a group. So in stratigraphy, I've already made a group. Go up here to data groups, and I'm just going to edit it so you can see what I'm talking about. And you can see a perfect example right here. This one, somebody just forgot the end parentheses, so I'm going to group it. Power BI is going to give us this name. You can change it. It's kind of long. Doesn't really need to have all that representation there. But those are pretty neat ways to clean up your database so that you can have something clean to show on your visualizations. So I think that is all I was going to show.
All right, thanks, Ashley. So moving on, Daniel, you ready to take over? All right, let's get going. Daniel Coots on R and Python tools.
Cool. So yeah, my name's Daniel Coots, and thanks to the AAPG Energy Minerals group for inviting me to talk about this kind of stuff. And so I'll be talking about kind of digital geology in Python and R, and kind of looking more specifically about kind of how domain experts can kind of rapidly add value to the kind of projects that you might be either consulting on or working on kind of at a company. So a bit about myself. I'm a recent PhD grad from the University of Calgary, Canada. And there I was kind of working on the west coast of Canada in the Nanaimo Basin, so the little kind of islands in between Vancouver Island and the mainland, walking around, rowing boats around, looking at the rocks. And during that time, I started working in VBA, but more recently moved into R and more more recently than that, Python. I completed Coursera's data science specialization. And then since finishing my PhD, I've been doing some freelance scientific editing and then a bit of geology-focused data analysis or data science. I'm interested in most subsurface geology kind of stuff like energy minerals, lithium, helium, ore deposits, CSS, and oil and gas. So this talk is going to be mainly focusing on freelancing in Python and R, and kind of looking at that through the lens of like the role of a consultant, but also kind of day-to-day work that geologists do. So I'll be talking about introduction to Python and R, some ideas on some domain-specific libraries, then kind of focusing to looking at how we can build tools really rapidly, and then how we can kind of streamline communication. So the role of a freelancer or kind of consultant in my eyes is that consultants are hired to fill a gap in a company or provide some kind of outside opinions. This is because people have domain expertise. So this might be your geochemistry, your geophysics, economic geology, data sciences, is whatever you kind of specialize in. And everybody here knows what they do better than me. And you're hired to kind of produce a product or provide a service. So this might be like data processing, data analysis, developing new methodologies or kind of training, and then kind of providing some kind of geological interpretation. And then kind of as these projects wrap up, you kind of communicate your results in the form of a report or map, a data set, a tool, whatever. And so all these steps and all these kind of portions can be handled in Python or R to the very full extent. And this is also stuff that, like, all these things are applied to general full-time employees as well. And so before we start talking about programming languages, Matt Hall would recognize this because this is a figure that Matt Hall and Agile Geoscience put together, kind of about what programming language you should use first. And I kind of want to leave this up here for a second to kind of demonstrate that there's a wide variety of programming languages out there. And there's some that are really fast, some that are used to kind of make apps or applications or kind of software packages, some that are generally difficult or used for specific purposes. But I'll be mainly talking about Python and R today. But there are many programming languages out there that you could use for any number of reasons. So Python is a very high-level interpreted general purpose programming language. Some of the strengths are that it's a very commonly used language for commercial kind of software. So this is like integration with QGIS or ArcGIS. There is an incredible number of really powerful geoscience libraries for like seismic and geomodeling. It is one of the dominant languages in machine learning. And some of the weaknesses is that it's not as fast as other languages. And then a general limitation, I guess, to a lot of programming languages is that there's kind of limited database access. R is a programming language that is dominantly used for statistical computing and graphics. There is a very kind of rigorous process for user-created libraries that are kind of hosted on the CRAN website, which is the Comprehensive Archive Network, which is where you mainly download these packages from. R is incredible for data wrangling and plotting, very compatible with other languages like C and Java. You can actually run Python code within it. But some of the big weaknesses is that it's often slower than Python and a lot of other languages, and that the data is stored in physical memory. So if you're working with, you house all your data in your RAM, even though RAM is really cheap, that can be a limitation. So when we talk about domain-specific libraries to actually do geoscience work, there's lots of different places that you can search for kind of libraries where people have written code to do various things. For R, there's cran, and Python, there's a few, like PyPy. And then there's also, you can download through GitHub and that kind of stuff. So I've kind of tried to make a quick little list here of geoscience specific libraries for Python and R for like spatial data handling, geochemistry, petroleum geology to do either like well logs, and I think we'll hear a bit about that later. And then some petroleum testing stuff, stratigraphic data if you do kind of sedimentology or geotechnical work, stuff for geomodeling and seismic visualization. So there's a lot out there that if you're kind of working on a specific project and are getting into Python or R, there's likely a lot of really powerful stuff out there. The one thing that I would recommend is just kind of starting to look into, as you're starting to use these or maybe develop tools with them, is to kind of look into the open source licensing that is part of these data sets or these tools that are already made. And there's a great, again, by Matt Hall at Agile Geoscience about kind of open source licensing and starting to wade through the legalese jargon of what's allowed with what. One of the best resources out there currently for kind of geoscience computing is Software Underground. So this is an online community that was started by the Agile Geoscience guys at Matt Hall. That is where they have a Slack channel, so like an online discussion board that is pretty much everything to do with computers and rocks, where there's channels on open source geoscience, Python, machine learning, pretty much any topic. And as has been mentioned a few times in the chat already, recently, over the last few days, there was the Transform 21 conference, which is a big geoscience computing conference put on by Software Underground. And some of the big, really interesting talks were kind of like processing gravity data with different packages in Python, or introduction to handling seg-y files through like just in a programming language rather than through any kind of software, some geological modeling. And so if you're getting into this kind of stuff of digital geoscience, this is by far the best reference, much better than any one package or anywhere that I could point you otherwise. So when we go to actually look at how to implement some of these tools and techniques or any kind of code that you've been working on, I think that building tools either for yourself or others is probably one of the best ways to kind of take that code and make it more into a usable product. And so it's essentially like building a very fancy function. And so building a tool or an app used to be very, very difficult because it traditionally required multiple programming languages like Python or Python plus something else. But recently there's been a lot of libraries that have been released over probably the past 5 or 6 years that allow you to more or less streamline that app creation process in a single language. So either Python for Streamlit and Plotly or R for Shiny and Plotly. And this allows you to produce a very elegant product with very little user interface experience. And then most importantly, it allows you to take any of that geological code. So maybe it's like taking a ternary plot or doing some kind of well test, and you can bring that into your app rather than just having it housed in like a little Python Jupyter notebook or something. So when you're building these tools, there's a lot of there's a large range of user interface and widgets, lots of plots. So we have some widgets in the top right from Shiny, so sliders and radio buttons and date ranges, and then some plots or maps that you can bring in as well. And then, so this is essentially coding or like hard coding a very specific Power BI you can think of. So just like Ashley was showing, kind of bringing these plots and stuff together, you can kind of fine tune exactly what you want, and that customizability or layout might not be readily available in Power BI. So one of the first things that I built in Python ever was a little app to kind of make a vertical exaggeration like angle figure. People that work in seismic and that kind of stuff will be familiar with these. And so I built this in Plotly, in Streamlit. And I would say that Plotly and Streamlit have like an integrated structure where you kind of write the user interface and the server side together. So in this little app, we have like a little header, and then in a kind of integer number field, and then a plot that changes as you change the vertical exaggeration. And then below there is like save.csv. And so the code behind it might be a little off-putting for some people who aren't very used to programming languages, but essentially there's a few different chunks. We have that title and that input at the top, some internal functions, all are kind of plotting code, and then a download button for the figure. And so this is extremely streamlined to build an app that does even something simple and be able to deploy it right onto the web really rapidly. And so if you had your functions that you need to do, say, geochemistry or some kind of seismic analysis, and all you need is to add paste a file into it and run a button. That might be easier for some people to do rather than kind of opening up a Jupyter notebook, because it can be a big step for some people. Our Shiny in R has more of like what I would call a simplified app structure, where the user interface and the server are separate. And they kind of handle different things rather than kind of writing them all together. You do write them separately. So in this case, we're doing kind of a k-means clustering, where we have our kind of title bar on the user interface side, this sidebar panel with some inputs, and then on the main panel, we have this plot. On the server side, we're kind of taking those inputs, and then we are kind of doing that k-means clustering, and then taking that output for that plot. And so these things are really powerful, because again, we can start to leverage our domain expertise and kind of skip through a lot of that kind of the portion of the programming that would be taken up by like a software engineer or some kind of app designer. So I've implemented a Shiny in an app to kind of take hand-drawn core data and turn that from this kind of graphical form that's often kind of just filed away, into a numerical kind of format that kind of retains the geologic information that we can now use for data analysis or prediction. And this idea originally came out of the Shell Clastics Research Group, and they implemented it in a MATLAB kind of application that was pretty clunky. And so I brought it into our Shiny. So in my Shiny version of it, we again have a sidebar panel with a lot of these kind of checkboxes. One plot of our stratigraphic section that you can kind of zoom in on a portion, and then you interact with this plot to actually start to put in beds or bed boundaries. Because it's made in Shiny, you can really easily do stuff like file upload and download buttons, which is great because I have no idea how I would program buttons or file upload and downloads otherwise, more or less. Again, this kind of reactive plotting or interaction where you can click on plots and you can kind of program the output. In this case, I was looking at recording the location of where users are clicking and kind of housing those in data frames. And then kind of getting users to generate their own categories. So in this case, people might have different facies names for different rocks. So instead of having a massive facies list that is more or less infinite, users can kind of create their own facies that are relevant to their project, or their own sedimentary structures that are relevant to their project, rather than having a huge predefined list. So again, not only is this a great tool to actually use, and I've used it quite a bit in a bit of my thesis work and a bit elsewhere at a few different companies, but it's it's a great tool on its own, but it's also a great tool because some of these processes are A, require a tool, but B, it really lowers the bar for kind of the required knowledge to do this kind of work. Geologists are a very analog group. Geophysicists are much more digital. Geologists are very analog, and so trying to do anything in a programming language can lead to some big kind of pushback at a lot of companies. So having kind of easy to use tools is fantastic. More on the dashboard Power BI side, rather than just like a kind of tool. I've created a number of tools for myself and some of the work that I've been doing as a consultant to kind of rapidly digest data sets. So this is kind of a dashboard for exploring geologic data with the spatial component, where I have reactive plots where I can change like the x-axis and y-axis parameter, maybe the color fill by another parameter, and then some spatial plotting where maybe the circle radius is for a certain parameter, and then the color may be another. So you can start to kind of pick apart these larger data sets. Again, you could bring in code to make ternary diagrams or any number of things from those outside packages, but I've been using it just for normal kind of data plotting. So when we talk about building tools, there's a lot of streamlined options out there for kind of making these tools. For Python, there's Streamlit, Plotly, and Dash, which are relatively simple. But then when you move into like Django and Flask, these are like the more involved general kind of packages that are used for like robust app creation. For R, we mainly have Shiny and Plotly. And these are really great for just making specific tools that you, the people that are contracting you, or your coworkers need. And I think that that's an incredible way that you can really start to add value through geologic computing. All of these packages have public servers that you can deploy apps to for free, but they're public. But you can also deploy them really quickly to private servers. For communication, which is like a huge part of what we do as geologists, especially as people doing technical work. As we start to do more in programming languages, some of the communication can kind of fall apart. And so I've been using a markdown language through R Markdown to kind of do all my communication. So I essentially have my R code in a notebook. And so I write whatever text I want associated with, say, a figure or a process. In this case, I'll get to that. So I have all my kind of code for figure creation and whatnot, and then I essentially change it from R straight to a PDF. And so this is kind of some work I've been doing on lithium for a company. And essentially I've been taking, so I can essentially take the code and hide it. I can provide a figure width and height, and then the figure will be automatically kind of input into the PDF. You can also, for R, you can knit to PDF, Word, HTML, or PowerPoint. So I could create all the slides I needed for this straight out of R Markdown, or straight out of like an R notebook. And it kind of streamlines the whole communication side, because you're no longer fiddling, you no longer produce your entire document, realize you have spelling mistake in a figure, then you have to re-export the figure, crop it, bring it into Word, do all that kind of word fiddling before you send it to PDF. And you can more or less just make your edits and continually work on these documents. And so, yeah, so for Python, that's there aren't as many packages for going to as many different formats, but there are some. So in conclusion, there's a lot of stuff out there for Python and programming for doing geoscience computing. Python definitely has an edge over R if you're looking to get into this sort of work. or this sort of kind of digital framework, because there's a lot of domain libraries that already exist. I love making apps for myself or for other people just to streamline their work or my work. And then I love working in Markdown because it really kind of takes a lot of the hassle out of kind of taking a programming language and formatting it into kind of a product or a report. So that's about it for me.
All right, thanks, Daniel. That was great. Moving on, we've got Christopher, who's going to talk about the Open InTech platform.
Yeah, and you can hear me okay?
Yes, sir. Take it away.
Right. I will share my screen. Okay. All right. So yeah, first of all, I'd like to thank the American Association of Petroleum Geologists and you guys for setting this up and inviting us to talk on Open Detect. So I will be presenting the Open Detect platform. A short introduction here on who I am. I work for DGB Earth Sciences. That's the company that's behind maintaining and supporting Open Detect. I have a bachelor's and a master's in geology from Åbo Akademi University. That's in Finland. I'm a geoscientist with DGB since 2011, so I just celebrated 10 years. And I have worked both in our Europe office in Netherlands, and I'm currently based here in Sugar Land, Texas. And I specialize in attribute analysis, sequence stratigraphy, and shallow and deep neural networks. I've been working for quite some time now with these shallow neural networks that have been around for quite a while. And also lately with the deep neural networks that we have been developing. And also getting familiarized with Python and things like that. That seems to be a hot topic these days. And I have worked on conventional and unconventional plays pretty much worldwide. So I've worked all over the place. So that's just a short introduction on who I am. Okay, let's move on. So this is the format of the presentation today. So we'll start with a little bit of introduction. Then we'll go over a little bit on loading seismic data. This is not always straightforward and easy, so I will show you some tips and tricks how you can do this hopefully easily in Open Detect. Then I'll talk about some things to consider when starting a new project. Then we'll look a little bit about attribute analysis and data conditioning. These are two things that you might want to do when starting a new project, especially if you're working with these sort of open domain data sets. Data conditioning might be necessary, and attribute analysis is one of the strong points, I believe, in Open Detect itself. So we'll have a little bit of a look at that too. And then I wanted to show you some new machine learning developments that we have been working on. What I like to stress here is that the machine learning stuff is commercial. There are commercial plugins that we use on top of Open Detect. However, what I will be showing here in the demo as well is that if you utilize the free datasets that we offer, namely the F3 demo dataset offshore Netherlands, North Sea, or the Penobscot dataset from offshore Eastern Canada, you can run all plugins in Open Detect without a license file. So I urge everybody to sort of download these datasets, download the software, and try out all the different plugins and play around with them that way. So with these new machine learning approaches, we have ways of imaging discontinuities, well log prediction, and we have some new approaches to horizon picking as well that I would like to show. So first of all, yeah, DGB Earth Sciences is the company behind Open Detect. Open Detect itself received the Distinguished Achievement Award from the SCG in 2016. This is an award we're quite proud of. So I'd like to mention that here first off. And Detect has been around for quite some time. It started as a sort of proprietary software for a client. And then in 2006, I believe it became open source, truly open source under the GNU platform. and hence the name OpenDetect. So it's been around for a while, and we have a fairly large user base out there. For the open source users, we don't really keep track of who downloads the software and uses it. You don't need to leave your email or phone number or anything like that when you download the software. However, we have a Google user group that we encourage all our sort of open source users to sign up for. And through sort of monitoring the traffic, we can see that we have the user bases in the thousands for this free version of OpenDetect. So it's a fairly active user community, and I would encourage everybody who wants to sort of test out workflows. If you run into a snag or you don't know how to do a particular thing, you can always type up a little email to this user group, and you get a fairly good answer, usually fairly quickly as well. So something to consider. Now, if we start with data and visualization, so Ashley's presentation talked already about the data sets that are available from their side. There is a whole bunch of sources you can use for getting free data or sort of open domain data. So what we do at DGB is we host something called Terranubis. It is a platform for selling. It's like a marketplace or for selling or just sharing seismic data or well data. There's BOMBG governments in Europe and in New Zealand, particularly as of late, they released data sets that you can acquire for free or for a small charge. I think the New Zealand data sets, they charge something small because they ship you a disk. And there's both well data and seismic data available. Then if you'd like to look into more advanced things with perhaps some interpretation, there is something that we also host called the Chimney Atlas, where we have collected numerous different studies we've done on fluid migration pathway studies around the world, where you can click around on a map and check out some presentations on fluid migration pathway characteristics in a certain area. Then there's also the virtual seismic atlas that's available online, where you can see different scientists have done different interpretations. It's a quite interesting website also to check out. And then there is, of course, free, ready-to-use software available, such as OpenDetect. There is also other ones, of course, out there. And there's a small link down here, web address from the Wikipedia page, and it's a comparison of free geophysics software. I also have this link at the end of the presentation. It's just a long list of stuff that's out there that is free for you to use. So as I mentioned in the beginning, all our plugins are available in OpenDetect if you use the F3 demo dataset or the Penobscot datasets. And these are available online on the Terranubis website. So this is a great way to test and familiarize yourself with more advanced workflows, sort of once you get past the first steps of doing the basic stuff. The F3 is located offshore Netherlands in the North Sea. It's a great data set with multiple different sort of geologic puzzles in there for you to solve. So it's a great data set that we also use in our training course. And there is also a complete online tutorial that you can do by yourself connected with this data set. So it takes you through the first steps of setting up a project, loading data, getting data in, interpreting the seismic, doing well ties, things like that, and all the way through all the different workflows we can do in the free part of OpenDetect. And then the second part of that manual takes you through all the different plugins that we offer as well. And then the Penobscot dataset is located offshore Eastern Canada in the Sable Subbasin. Also a great dataset if you'd like to look, especially if you'd like to look at some sort of pre-stack functionalities in OpenDetect. This is a great dataset for that. We offer that as a separate sort of download because the files are rather large. This is all stuff you can download on Terranubis. This is how the web page looks when you go to the website. I have a link again at the end of the presentation. You get sort of a world map, and these little red areas here is where you can click around and look at the different data sets that are available. Currently, there is a whole bunch of them here in the North Sea in the Dutch sector. F3 is one of these. It is an open domain data set. that you can download from here. So this is something you can check out on your own time. Now let's get into loading seismic data. This is not always straightforward, as we will see. Currently we're dealing, or we're supposed to be dealing with something like Segway revision 1 or 2. This is often not the case. Especially we found that old 2D data can be very tricky to load. The segways might be messy. Also for 3Ds, the header information might or might not be correct. So you need ways of sort of manipulating your files, but also investigating more deeply, like what is in that actual file. And also there are tools available for you to QC once you have loaded or what you actually are going to load. You can QC that beforehand. So in OpenDetect itself, we usually set up surveys. Most typically, I'd say we set up surveys, a new survey from.
Set timer for 1 minute.
We usually set up the surveys from Segway files. So we scan the Segway files. We can, of course, also enter manually and do all these kind of things, copy from other surveys and so forth. OpenDetect works in such a manner that we set up a data root that's somewhere on our D drive, for example, and then we have a folder where we want to have all our different surveys, and then all the different surveys show up in this window that you're greeted with when you open OpenDetect the first time. So you have the list of available surveys. We can do some basic survey QC here. We can see the shape of the survey. We can see the inline, crossline range, Z range, and so forth. So basic QC already possible here. Now, if we move on, setting up the survey is done with this little plus and a blank sheet icon up here. It's pretty much the same workflow if we go set up a survey and scan a Segway file. Then if we do an import seismic data and Segway, this is what you would do then later after you have set up your survey based on any sort of Segway file. You can also bring in other Segway files into that same survey. This is the GUI that shows you what the software finds when you select the Segway file. So many times, if everything's idealistically in Segway revision 1, it will show up here as Segway revision 1. And you don't have to worry about anything. Everything here looks really good. Inline ranges, crossline ranges all make sense. The Z range makes sense. But this is often not the case. The software will flag this as a revision 0, no revision at all. Then in that case, you need to set the inline crossline byte locations yourself. Now, we can use this magnifying glass icon here, sort of investigate further what we have in this actual file. We can see the header information. Many times this header information is very limited, or it might have wrong information. So in that case, we might want to just browse through the file itself and say, if I'm looking for an inline, for example, I might look for this sort of staircase behavior in the sorting. This is a typical thing for inline sorted data. In my case now, I found it in byte location 9. If that's not enough, if our Segway is damaged somehow, it's corrupted, we can also manipulate this Segway file. Type in for any of these trace headers, we can type in a formula. We can copy from other trace header locations. So there's a very flexible tool to sort of manipulate your actual Segway file. And then we output that as a new file. Many times also the data is sort of messy and we might want to just scan that Segway file and then do a resort. And that can also be done with the manipulation tools in OpenDetect. So we can create a new sort of fresh Segway file from an old corrupt or damaged Segway file with this tool, where we just scan it, resort. Now, things to consider when you start a new project. There are some tips and tricks here that I hope you will find useful. I would personally recommend that you always preload the data set that you want to work with. This speeds up visualization, also attribute calculation, things like that. So keep in mind always to preload your data. Of course, here we need to work within the capabilities of the system that you're working with. More RAM is always better. As with everything, good video cards and high-end gaming machines are always the best bet when working with seismic, but there are ways we can work with the capabilities of your system by doing scaling and so forth, decimation, even if it comes down to that. Then I also recommend usually personally that you create work areas if you have large surveys. Focus, sort of look at the big picture and then focus in on smaller detail by utilizing the work area, or this is called probe in other software, I'm sure, where we can just minimize the area and sort of focus our efforts more effectively. And then in OpenDetect Pro, we have a base map tool that I think is sometimes a little bit overlooked. Use this base map tool. It's an interactive base map tool where you can pop up 2D viewers, you can add in lines, you can scroll through these guys, and it's a synced base map. So everything you do in your base map will also reflect back to your 3D scene in OpenDetect. Right, so if we go to preload our data, I will show you this in a demo here in a little bit. We want to preload. We have the option here, in case we are dealing with large volumes, we can scale the values down all the way to 8 bits for visualization purposes. And we can do the automatic scaling of the values by just scanning some example locations. And the software will actually suggest to us to scale from and to scale to. 8 bits, of course, cannot contain infinite number of digits, so we need to scale this down. So this is all tools that are available to you, so you can work within the bounds of your system. That's preloading and things to consider when starting a new project. Then let's go a little bit into attribute analysis and data conditioning. As mentioned, I find that this is one of the stronger points in OpenDetect. The attribute analysis per se. Often we find that publicly available data, which may or may not be old, might sometimes need data conditioning. You might want to apply in some sort of gain correction. We can apply structurally oriented smoothing, footprint removal, anything like that. It's always good to sort of start off with sort of conditioning your data as much as you can. There is post-stack tools that you can use, but also pre-stack is available. You could do some filtering of pre-stack gatherers and so forth. Another strong point in the attribute analysis is that in the OpenDetect attribute editor, we can create chained attributes. So we can do attributes by using other attributes as input. We have quick ways to create relative impedance, for example, and here also something to keep in mind is that you can link your own Python code, MATLAB code to the attribute editor, so you can do stuff in Python or MATLAB and then bring it into OpenDetect in the attribute editor. There's also links to Madagascar for processing, GMT for mapping, and so forth. These are all free links that you can set up in your own OpenDetect. They don't cost anything, they're just additional add-ons. We also have on the website a attribute list. It used to be called the attribute matrix. This is a great way of looking at what's available. And here we aim to sort of help you decide what attributes to use and not just blindly apply attributes that you don't really understand what they're doing. So we have collected all the attributes that are offered in OpenDetect in this list, where you can read more about them, see what they actually do, and understand what they do. And there's also links to references at each of these boxes where you can check out publications that talk about these attributes and so forth. So you can really learn about what the attributes do, why you should be using certain parameters and so forth. So this is a great tool as well, available on the website. So most of the attributes that are in OpenDetect are actually under the Freeware version. So there's a big list of attributes you can use in the free version of OpenDetect. Then these attributes can be sort of enhanced by utilizing plugins such as dip steering mainly. We can sort of steer the attributes to look along the grain of the geology instead of just along Z slices, for example. We can chain attributes in mathematics. So I mentioned you can use attributes as input for other attributes. Also with the mathematics attribute, you can use any sort of logic statements, expressions, and formulas. You can use constants, you name it. We also included some time back a rock physics library in OpenDetect. So this is included. You can access this rock physics library directly in the mathematics attribute. And of course, you can create your own statements as well with the mathematics attribute. And then we have an intuitive attribute editor that allows you to sort of test your parameters beforehand. Nothing is stored on disk until you decide to write out that to disk. So it's an interactive way of testing your parameters. This is the attribute editor. So this is how it looks. We have a list of available attributes here. We can add attributes to a list and we can evaluate. So we will actually have a look at this in the demo I prepared for you guys. We can use an interactive slider here to see what happens when we change parameters to this particular attribute. Now, in the case if we have chained attributes, saying that we have attributes that are used as input to other attributes, we can use the second option here, which is the cross-evaluate parameters, where we can change the settings of the attributes that are either used as the input or the second attribute that's the sort of the derivative attribute. So there is these evaluation tools that we encourage you to use. So data conditioning, this particular slide is from the F3. We will have a look at this in the demo here shortly. This is our original seismic that comes, that can be downloaded from the website. As you can see, there is quite a bit of incoherent noise in this data set. So what we want to do is we want to apply a structurally oriented filter to this. We can see if we browse through these two volumes that we just remove the incoherent noise and sort of any sort of horizon tracker or anything like that might work a lot better on a data set like this when compared to the original noisy seismic. Now, by using the mathematics attribute here, I have been able to extract the residue. So what was exactly removed? As soon as you sort of start seeing structure in here, you know that you've gone too far. I'll show you this in the demo that we will go into right now. So let me pause the presentation for a little bit and let's go into OpenDetect. All right, so here we are in OpenDetect. I have not loaded anything. This is the F3 demo dataset. Let's go ahead and add an inline. So I will select data. In this case, this is pretty much the dataset you get if you choose to download the whole thing from Terra Nubis. We have the original seismic, but we also included some other useful volumes that may be of use to you if you decide to go with the full version of the F3. We can load our original seismic on this. So this is what we would start with. As you can see, again, there is some incoherent noise in this. And in order to remove this, I'd like to apply this structurally oriented filter to this data set. What I can do is I'll first add a blank attribute on this line. I can close this for now. And let's go into the attribute editor. This is the calculator icon. We can go through here, or we can go through analysis, attributes, and 3D. What I want to do here is actually what it is, the structurally oriented filter I'm applying is actually just a volume statistic attribute where we want to apply a 0-0 time gate. We don't want to smear in the Z direction. We just want to smooth out in the horizontal direction. Output statistic here, you can decide if you want an average or a median. We usually recommend what we call a dip steered median filter, because the median is a edge preserving statistic. So it's better to use that unless it's a very noisy data set where you actually want to average out things. But we also offer directly in the attribute editor here, as you can see, the list is fairly extensive, a dip steered median filter attribute all its own. All you have to do here is select your input data. So we'll select our original seismic, which is going to be the input. The step out we need to set here, but we don't really know what we want to use to step out. So we'll leave this at 2 and 2 for now. We want to evaluate this parameter. And then the steering data here, we need to set a steering cube. It's a cube that contains the dip and the azimuth of the seismic reflectors. So we select our steering volume here. That one. Here we also have the option to output either the filtered results or the residual. So we can add filter. So let's call this media filter. And add as new to this list. What I want to do now is test the parameters for the step out. So what I will do is I will click on the evaluate icon here, evaluate attribute. I will set the initial value here to 0 and 0, so no filtering whatsoever. Increment of 1 and 1. So for each slice I add here, I will add 1 inline and 1 cross line in the step out. And then we can do, say, 5 steps. We calculate. This is done on the fly, so nothing is stored on disk except the attribute definitions once you save this attribute set. That's why it takes a little bit of time for this to compute this. It's computing 5 steps with increments of 1 and 1. Once it has finished the calculation, we can zoom in a little bit here and see what happens when I use this slider. So when I slice toward the right, you should be able to see what this attribute actually does. So it applies smoothing. So now our step out is 2 and 2. We can go further and apply something like 3 and 3. Once we find a parameter here that we're happy with, we can click on accept. Once I do that, the attribute here in the list here is updated to that step out that I just accepted. So 3 and 3 might be a little high. Let's go 2 and 2. I mentioned chaining attributes as well. So if I want to do the residual, I could do it here by just selecting residual here and typing in residual. But we can also do it with the mathematics filter, or the mathematics attribute, sorry. I will just browse here to mathematics. Like so. And here you can see, this is the link to the rock physics formula, the rock physics library. Here we have a list of different formulas that you can use, tried and tested formulas. You can, of course, edit these, type in your own, and so forth. And this I just want a simple operation. I want to subtract the original seismic from this dip steered median filter attribute that I just created. So I can type in here original minus smooth. So you can type in anything here, cats minus dogs, it doesn't matter. You click on set, and here we need to set what to use for original. Of course, here we want to, for original, we want to use the original noisy seismic. And for the smooth part, we want to use the dip steered median filter attribute that we just created. So now we're using this attribute as sort of enchaining these attributes in this mathematics attribute. And I can call this residual. Add as new. Then we can add a third attribute on this line, and then select the residue from this list of attributes, residual. And then it's going to compute again on the fly. Nothing is stored on disk yet, just the attribute definition itself. Once we're happy with our filtering, we might opt to write this to disk.
Hey, Christopher, I'm sorry to interrupt, but
Yeah.
In the interest of time, can we wrap it up after this and maybe take up questions people have at the end?
Sure, certainly. Yeah, I'll wrap this up because I had this in the slides already. So I have 3 minutes left, or
We're running a little over. So
Okay.
yeah, if you want to wrap your slides up, we'll move on to
okay,
Dave's
I'll
talk.
skip over the machine learning part here.
Yeah.
If you want to learn more about the machine learning workflows that we have, I can recommend you to visit our website. I have useful links here at the end of this presentation, where you can go and you can read up on these machine learning methods on your own time. So sorry for taking up too much time.
Oh, no problem. I think we've all run a little bit long.
Okay. Well, thank you very much. And I will end here. And I guess we'll do the questions at the end, as you mentioned.
Excellent. Thanks, Christopher.
Thank you.
Now for our final speaker, we've got Dave Thule. And I know you didn't make it for our dry run, Dave, but I hope you can give people a quick intro to who you are and what you do, and then get into your talk.
Yeah, for sure. Thanks, everybody. My name is David Thule. I'm a geoscientist. I run a company called Geolumina. We are focused on using computer vision for subsurface analysis. We kind of believe in training computers to see like geoscientists see. Today, I am showing an app that is kind of complementary to a set of our core facies tools and some other things that we've made. It's just an LAS facies clusterer. I think anyone that follows like the LinkedIn programming and geoscience scene has seen like the KNN log mixture model or the, whatever, right? And I finally got sick of redoing it in a Jupyter notebook over and over and over again to use it as a tool. So like what Daniel showed earlier, we do full stack web development in Python. So we're using Flask, we're using Dash, we're using Plotly, we're using Python, and we're using Lazio, kind of all the packages that make Python geoscience possible. And we decided to just like make this tool open source so everyone will be able to access this. I think I'm sharing my screen now. You guys can all see it. So we're just starting to deploy all of our stuff onto the web. So you can go to apps.geolumina.ai. It is not like fully functioning yet. So if you want to sign up, we've actually restricted like user sign up, so you can't make your own account. But if you want to email me, I'll make you an account and you're going to have immediate access and play with it. So in the future, we'll have a whole set of apps in here that do image and geology based things. Our business model is really about enterprise customers, so individuals and freelancers. We like to give lots of free tools to that I think will change your life and make geology much more fun. So let's just jump into it, and I think I can adhere to the 10-minute guideline here. You just log in. I was already logged in, so it's not asking me to do it again. So everything's user authenticated using a third party, so it's all super secure. We do have lots of help pages. So like all of our apps are simple and do one thing. Like we try to make them not do 50 things. We try to not make them be hard. And we try to recognize that a lot of this is a different approach to geology than a lot of people in the analog world are used to. So you can always click these links and we give you a pretty deep dive, but also brief on support. Like why do we use the models we use? How do you pick parameters? So everything that's got a blue link, you can click and learn. So our LAS facies model uses a Gaussian mixture model. We do that because it allows you to know both a classification group, a hard class, as well as a probability class. And so you get to know where things sit. So I just loaded the demo data set here. You can also upload LAS files. We have pretty complicated error handling. So hopefully, even if things are screwed up in your LAS file, you should be able to load it. I've tested, I think, like 2,000 LAS files from different file sources and providers and provenance. So, but if you do come up with one that doesn't work, you can hit us with a bug report button up here, and you can tell us what's wrong and why it's not working and what error messages are coming in, and we'll fix it. Usually pretty fast. We do all our development in the US, so like if you hit us at 11 p.m., you know, it's not going to go to like Poland and get fixed by a bunch of people that are working in a coding sweatshop. So, you know, we ask you to like bear with us and understand that it'll take some time. So like I said, what I'm doing here is I'm just selecting the demo data set, but I could drop a new data set in, and then you see the app advances you to this filters tab. Hold on one second. When I click too much, you know, the slow servers right now, they kind of get a little bit worked. So give me 1 second now that I've clicked 55 times on different things. So again, you know, select or upload your data set. This is a lazy D well. That's a pretty commonly known Codell and Niobrara core in the Denver Basin. It's just a really nice and easy one. The logs are good and there's a lot of variety. So it's a little bit slow loading here because what it's doing is it's reading through all of the well log headers and it's picking what we think are the best ones to do a facies model on, or, you know, like log facies. So you can see in our interactive box here, there's a set of curves. So it's selecting a deep resistivity, an N-Phi, a gamma ray, a rho B, a PE, and that's it. Then I'm going to click update curves and it's going to plot the plot here. So we're always working on this like definition side because everybody's log headers are screwed up and that's terrible. So it's really hard to make it plot a lot of things automatically. So if it can't find stuff that it likes in your log, it'll just pick like the first 5 curves and you can just turn them on and off with a checkbox. So you can see here, now we have a depth plot of all of the curves. And the next thing we need to do is just scroll down to a depth filter. We want to apply our model over some depth range. We're just going to choose like the Niobrara, Pier Shale, Niobrara kind of Sharon Springs or transition. And I'm just going to hit submit. And it's going to do some things in the background. Once these loading bars stop loading, you're free to select how many facies clusters you want to make. Again, we have a whole tutorial about like how to choose the right set. You know, like this is obvious, but you know, be a geologist here. Like, you know, use geologic reasoning. Like the right answer is almost always 5. You know, at first we made this tool to do like, you know, you could do anywhere from 2 to 25, but like the pre-calculation and stuff really slowed everything down. And we realized like it was totally useless on a lot of logs. So like we limited that down a little bit and said, you know, like be a geologist, don't be a lunatic. Like common sense is good. So, you know, I'll just pick a facies group number. I'll pick 4. So it's going to break this log set into 4 facies. Or 4 clusters, really. All it's doing is cluster analysis. It doesn't know what type of rock it is. It's not doing petrophysics. It's doing dumb clustering for dumb geologists like me. And what we, you know, so here it adds 2 tracks. You got the facies and the probability track. Let me zoom in. And I'll zoom in again. I'm clicking and dragging. So you can see this is facies 1, it's purple. Facies 0, Python 0 indexed, and we haven't changed the numbers yet. And you know, so each color is a log grouping. And then in the probability track is telling us how certain that grouping is. So in this case, you know, this transition to the pure shale, it's really certain that it's different from anything else in the log. So it's 100% probability. But when it's picking clusters kind of down here in the more marl and chalk transitional zones, it gets a little confused, right? So you know where you need to focus your time and energy. There are a couple augmentative plots at the bottom. The one on the left is showing the first principal component versus the second principal component, and then it's colored by facies. So you know that's like what's accounting for the differences. and there's a feature rank one so that you know which logs are contributing to the grouping, right? So in this case, you can see that principal component 1 is mostly made up of that neutron density log, the gamma ray, the PE. And you know, this isn't a highly technical tool. It's a way to get fast groupings. It's a way to deal with well logs and uncertainty. And you know, like every now and then someone says on LinkedIn, like, what do you think of my chalk versus marl facies model? It's like, yeah, it's probably good, like, you know, but do it this way too, and get after it, right? And I see Daniel's laughing because he probably read the same post that I commented on. And like, I think this is cool, right? And so we have several releases coming up. So right now it does single logs. So next it's going to do batches of logs, right? So you can put 10 or 15 logs in there. So like, let's say, here's the scenario. If I have 3 cores and I know what the facies are in those 3 cores, I want to make a model from the logs that matches them. So I'll put the 3 logs in, I'll create the facies model, and then I'll apply it over to the 10 wells that I don't know by matching the log curves to the well logs to the core photos. And so like, we made this to build our tech stack for the rest of our image-based apps. So like, we have coming out a core facies app that does, you know, what's the lithology from the pictures. And we have a bunch of different models from different depositional environments. We're going to roll out ichnofacies one, a burrows one. They're all kind of contingent on how good the visual resolution is, but they're awesome, right? Like, you get 80% solutions in seconds rather than ever driving to the core library. Then you get to go and drive to the core library, and you get to you know, tell the smart people over there, hey, I only need to see this 8 feet of core because everything else I got locked down, right? And this really matters in like the Green River when you have to pull 1,000 feet of core to figure out what your life is, right? So this is just the early iteration. It's a simple tool for simple geologists. It's great for clustering things. It's awesome for settling the debate of where's the transition between the Niobrara and the Pierre Shale, because if you set the clusters to 2 and you pick the depth interval over which it changes, it picks a really nice top, and you don't have to debate over whether you put it on the bentonite or you move it to a different thing. Just let the statistical thing tell you, because what it's seeing is the change of carbonate presence. So you can do all kinds of nice stuff with a really simple tool that makes your workflow much faster. So that's what I have. It's a simple tool. Oh, there will also be an output. Also in the next iteration, you'll be able to change the facies names. So right now it's just numbers, but there will be a little toggle box. So you can say facies 3 equals marl, facies 1 equals chalk, you know, whatever it is, you can just write it. And then you can export LAS files out of here. So then you can dump it into whatever your actual software platform of choice is. So that's what I got, everybody. Yeah, Justin says, is there an export feature for the results? Yes, there is. It exports an LAS file, so you can load it in everywhere else. We'll probably put in a CSV export too, just because I never know where people are going to work. So that's it.
Yeah, some of us still live in Excel land, so you know.
Yeah, we can do a CSV. I'll put that in there special for you, Justin. No problem.
I appreciate that, because I've got some Gulf Coast cores I'd like to dump in there and see what they spit out.
Totally. So I guess I would say one other thing, which is like, I think Daniel's got a great point. Like, you can learn how to code. It's not that hard. Our personal ethos is that every geologist doesn't have to be a coder. If you want to, you should. If you don't want to, we're going to release a ton of these tools that get repurposed a lot for free. So, you know, like this one was built off a lot of people's different demos of how to do KNN clustering. And we made some little tweaks, we made some changes, and we front-ended it. And you'll see a lot of that stuff coming from us for free over the next couple of years. So
that's great. And you know, the more online tools that are out there people can kind of play around with, the better, I think.
Yeah.
So appreciate that. All right, guys. Now it's time for the Q&A portion of the show. And if anyone wants to stick their hand up or put a question in the chat, hopefully our presenters can address your questions or point you to resources where they can be addressed. So the floor is yours.
I tried to raise your hand. I just wanted to say before we start this that thank you. And I know there was, you know, you look at the participant number and you look at the number registered. I just want everybody to know that a lot of people registered just to keep track of this, and that the views and whatnot, it doesn't reflect the amount of people or interest, I guess. It kind of shows and accentuates the way that we were talking before, how these types of things are going to work in the future. And that's that a lot of people are going to tag it, watch it later. And so the viewership doesn't necessarily reflect the reach.
And yeah, and it kind of comes back to something we talked about before we started. The virtual meeting paradigm is going to be, it's going to be great for a lot of folks, you know, being able to watch presentations when you have time, because, you know, as Mike Campbell was saying, going to an all-week conference is exhausting. And sometimes, you know, particularly as somebody who's more on the academic side, GSA meetings are great, but man, they will wear you out. And half the stuff you see while you're waiting for the stuff you actually want to see is not always super useful. Sometimes it's interesting, but if you're there for work and not for interesting, you know, sometimes you just need to get it done. So anyway, someone had just asked Dave something about loading rasters. So you can load rasters in this tool?
No.
Okay.
So I think the question, I can't tell if the question is about picking tops on rasters or digitizing rasters. So maybe Raleigh wants to clarify.
Yeah, can
you hear
we
me?
Yeah, hey
Say that
Raleigh,
again?
so do you want to clarify your question?
I was thinking, well, two things, kind of either picking or just kind of image recognition type stuff, not converting it to a curve, but like pattern recognition from that you can use for
From an
picking
image.
or for you know like the pay looks like this, let's say, and you want to scan thousands of things, maybe predefined the interval or whatever.
Yeah. So like I said, we do a lot of image-based processing in tool creation. And so we have started tackling this problem. It's actually a lot harder than you think, not because training the models to see the right pattern is hard, but because coping with the diversity of log structure is hard. And so the way we've actually dealt with that is we remove almost everything that's in a log. The grid, the spacing, the depth numbers, and we just leave a trace. And then we scale that trace in X, Y, and space. And then we pick from there. But damn, it is really hard because of the diversity of log display. So if you have a more uniform set, it can be really fast and powerful. But if you don't, it's pretty brutal. I actually think that like getting it to work on raster logs is the wrong solution. As an industry, we should just get everything digitized and we should all have the same logs and be done with it. Like if we took all of the money we spent to redigitize the same logs every couple of years as an industry, we would be, we'd probably save a couple $100 million over the last 30 or 40 years. And so that's ridiculous. So I think there are a lot of people doing good work there, and we are making a digitization tool that'll hopefully, Neuralog is like the leader in that right now. And, you have to pay quite a bit and it's not super automated. So hopefully we'll have a better solution to some things with the new image processing capability that the world has just over the last couple of years. And then we'll just digitize everything for free and give it to the world. Screw it. Like, yeah. I don't think you should make money off digits on logs. That's dumb. So everybody follow me on LinkedIn and cheer me along. Yeah. Because we're out on a capital raise for my company right now. And so just like thumbs up everything I say and we'll make that tool exist.
I think we can do that. One quick thing I'll note related to that. One of the tools that the tool I talked about on the first Freeware for Freelancers, the web plot digitizer, I've actually had decent success with that, taking raster logs and getting digital outputs. It does take, I mean, you can automate it to some degree, and it's, it's still a little more hands-on than like an automatic tool. But if you're desperate and you have the images and you need it in a numerical format, and you don't want to trace it in Illustrator or some other tool, that works reasonably well. I've been using that on Maori data from the Wind River Basin recently, and it's pretty effective. But to Dave's point, man, the quality of log rasters is so variable. It's really a frustrating problem. And if somebody comes up with a software solution for it, that would be fantastic.
Oh yeah, I agree. There's a lot of state data out there that's only in raster form, so it's
it's
a problem that
hopefully
isn't
that'll-
going away. So yeah.
Right. Yeah,
Until
because
David
no one
takes
has any
over.
money to do anything about it.
Well, there's lots of people that have the data.
Yeah.
They pay a lot of money to digitize it, but
Right.
Yeah.
So someone just asked in the chat, Jan, that yes, there is on the EMD YouTube page that Mike Campbell's nice enough to curate for us while APG figures out their issues with web presences. And there'll be a link to that in the list of links that I'm going to send around, or that me or Mike will send around in the next day or so. But yeah, so that's out there, and I would suggest going straight to the web plot digitizer webpage, because the creator has some really great tutorials and information that you can use. Apparently, and because I don't really use R or Python, I haven't tested this myself, but you can integrate his digitizing tool into those software environments and automate it that way. So free cross-section tool. I was wondering how long it was going to take for that to come up. Does anybody have an answer for this?
It's yet another thing
they're
we're
working on.
on.
One was part of the hackathon at the recent Software Underground project that some folks put together. It's early days, but they're making progress.
Yeah, we've been banging away at one too. It's a non-trivial task because of the problem of raster and LAS logs. Actually, like if you only had to handle one or the other, it becomes much simpler. But it's not, like now I know why no one's made one after banging away at it for like 3 months. It's like, oh man, I don't feel like I made any progress. There's code and it works better, but man, it's hard. So yeah, sorry. The cheapest one is Golden Software Stratter, and I think it's really great for what it is. And if you're using all of these other tools, it's really effective because it's not great at making cross sections from like everything on a map, but it's really good if you know on where you want to work and working on a small piece. So like if you use Power BI and ArcGIS or QGIS to narrow down your work area and then make a final presentation kind of product in Golden Software's Stratter, it becomes really powerful.
Well, in my judgment, it always starts with the geological interpretation. And I remember up until the last few years anyway, when people wanted to do maps like cross sections or other things and try to run it on a computer, it would always give you little circles because the program would default out that way. And yet on cross sections, I think the key to doing cross sections is if you start with a geological interpretation like a scan model, and then punch in the computer capabilities and let it spring from that. I mean, you can do it generally to set general parameters, but no wonder the computer doesn't know what to do, because it's actually guessing what we would do. If you get my drift.
Yeah, and they're not very good at that yet, luckily for us.
Yeah.
And I can add to that. There is, if you just want to test it out, we have something called the Weld Correlation Panel in OpenDetect. It's not per se a free part of OpenDetect, but again, with the F3 or Penobscot datasets, you're free to test it out, see if you like it. We can also set you up with an evaluation if you'd like to try it on your own dataset.
Excellent.
Chris,
Mike,
can you
maybe-
talk a little, I was gonna add
Oh,
a
go
little
ahead.
bit more about on OpenDetect. Is there's like with different volumes of seismic, how it handles memory, and if there's things that we do using it that breaks it, or how to like workflows that you've kind of come across that we should think about when looking at that software?
Yeah, so I mean, like I mentioned already, the preload is a very good tool. So preload as much as you can within the realm sort of your system capabilities. If you're dealing with large volumes, you can preload as 8-bit or 16-bit instead of the default 32-bit. It's only for like visualization purposes. Then when you go on to do detailed AVO analysis or something, then you can always revert back to your original data. But for visualization, yeah, I would say preload. In case you're dealing with very small amounts of RAM memory, because we do preload into the RAM memory, we can always either scale, and if it comes to that, we can also decimate volumes, just so you can quickly visualize. And then also, of course, these probes that I talked about, where you can sort of pinpoint an area of interest and work within sort of a smaller little sub volume is very useful as well.
Is it all running through RAM, or can it use and the CPU, or can you use GPU processing?
Well, yeah, we use both, but yeah, so if you just load your seismic data without preloading, it reads it from your hard drive, from your disk. So in that case, I mean, yeah, inlines show up quickly, SED slices not so much. That's where the preloading sort of helps. It indexes the volume and helps you bring it out. And then for processing, yes, some processing uses like multi-threaded CPU stuff. Some of the stuff you can also run with GPU, especially in this new machine learning toolkit that we have. A lot of it runs on GPU as well.
Great, thanks.
One thing I should have mentioned on the USGS data sets, well, I did say that it's all meant to be machine readable, but most of what you'll find is going to be in like XML format. And so I guess there are occasionally like ARC layers you can download and things like that, but for the most part, it's going to be XML. So if you have a way of inputting that directly, you can do it straight from the website, from what I understand. See, do we have anything else in the chat? We've got some good links in here. Appreciate people doing that. Anybody else have a question or comment, suggestion?
I wanted to make a quick comment before you close or whatever. And that's that, there's not a lot of people left on this particular Zoom presentation, but it's this jump from platform to widgets or whatever. I talked to Kurt a little bit about it. And that's kind of the next thing we're going to probably be seeing is a lot of these things that are being built by individuals. And it's important as a community, scientific community. And that's kind of what Software Underground did with their last webinar was, kind of bridging that gap between the programmers and the people that are able to put this stuff together and the end user. And I hope to see more cooperation on that level. And I mean, we would be capable of so much more once these things are kind of developed. It's neat to see this happening. I really like it. So thanks to everybody that participated, everybody that's listening. And yeah, I hope to see more cooperation in the future.
Yeah, just to kind of dovetail on that, I don't know if this has been done in the past at regional or national APG meetings, SEG meetings, SPE, various other organizations, but I don't think it'd be a bad idea to have sessions where people present software tools they've developed, or even some of the presentations that have been done here and in the previous webinar. I think you've got to, do more than just present scientific findings and then have $1,000 workshops at some of these conferences. Because if you've already paid for your registration, it'd be nice if you can learn a little something that's more tool oriented than, maybe research oriented at an APG meeting where you don't have to pay extra to sit in somebody's workshop. And I know that a lot of those workshops are great and they're more in depth. And I don't want to cut into APG's bottom line any more than it's already been cut into, but also a big advocate of, providing services to the membership. Because otherwise, why would you keep paying your dues? So
you may find that that you run into a lot of structural things more than you think. There, I think Matt Hall is really interesting for their group for how much they've pursued being open source about what they're doing. There's also an awful lot, I think, in line with what was just said about trying to connect coders and tools. The workflows that we're used to doing, as you start getting more digital systems that we can use, and you have like a machine learning tool running in parallel that's detecting things that are more rigorous than our intuition, as flawed as it is, recognizes, we're going to start improving old workflows in geology and subsurface work. And that's really, I think, where digital creates value for us. But it's a challenge to find the people that are thinking well about what we think we knew in the past, what might be wrong, and how digital tools can help us go further. And that's not just a problem of giving knowledge workers widgets that they can use. It's really finding out the whole workflow is changing as the widgets change the way we interact with data, and the interpretation gets different. And that's something that I found the conversations that APG and SBE are having they're having a difficulty really figuring that out. Most of the people are talking about, how do I scale up an old workflow? And that's it. And it's hard to get, it's just a conflict. And I don't know what's the real source of it, but I think looking at the success of a group like Software Underground suggests that there's a void that exists that they're filling. And our group's trying to fill that a little bit too, but promoting a stronger conversation and really advancing what this stuff can do to help us be better about our work.
Yeah, well, some of it's just inertia, and the same issue is coming up in terms of like one example from my work is mineralogy data. For the longest time, you were lucky to have a sample maybe every 10 feet from a core. Well, now we have shortwave infrared scanners where we can get 0.5 millimeter resolution data on 1,000 feet of core. What the hell do you do with that? How do you even start to work on that kind of data density? I put out a paper on the Niobrara, one of the cores we had scanned a few years ago, and it barely scratches the surface of what you can get out of these data sets. And how do you put something like that into a paper? How do you communicate it? How do you show it? And then, like our core research center, we've been wanting to take the data sets we've collected and serve them up, but we don't have the infrastructure. And our core curators are great with rocks, and they're great with saws, and they're great with people. They don't know anything about shortwave infrared or machine learning tools, or even just web service of high resolution photos and lithology data. They could learn, but there's a ton of transition. There's the energy transition, I guess, the big buzzword. There's more to it than just changing resources. Some of it's also changing the way we work, like you were saying, and there's a lot of facets to that are not really being addressed. Mike, you had something?
Yeah, I was just going to say, and I don't know how it would be received, but I think that the logical next step as a scientific community, or as earth scientists, I'll just lump us all together, is for us to take smaller scale problems and actually provide solutions and deliver these solutions to whoever. We have the tools, we have obviously the crew to do it, and we all have our specialties. It'd be nice to see, taking the EMD structure, the AAPG EMD structure with its counselors, regional counselors, addressing those regions, finding out what problems exist that are solvable, and presenting that as a conference. We're all going to solve this one problem at this conference. Come to this conference, we're all going to work together. Doesn't cost you anything. We're going to solve this problem, package it up, and maybe hand it to the government and they can do with it what they want. But we provide them a cradle to grave solution to an issue, and we provide the insights and the tools and everything else at no charge. There you go. Do with it what you want. We're going to move on to the next problem. And you guys, you can choose to ignore it or you can choose to use it. And I think that would be, you know, something that would be a great next step.
I agree, Mike. And I think one of the first things that would be nice to work on in that challenge would be access to free data sets, not just from the USGS, which is great, but from all the states. I mean, if you've gone to those state websites and tried to get data out, it's a nightmare, okay? But if you had something that presented a unified structure on how to find data and download it, that would be really helpful for people like me who don't have access to proprietary data sets right now to play with.
Yeah, a data standard would be great. That's and that would be. I don't know how many days of a workshop you would need to figure that out, but
There's that
I guess like
OSDU
Mike was saying, if
group,
we
they're
break it up
still
into
going and
parts,
they haven't solved it.
yeah. No, it's tricky. And there's actually there's a group at Stanford who's looking at doing that right now with geochemistry data for rocks from all over the world, all different ages, and trying to integrate those data sets into one publicly available package. And you know, it's a big task.
You can
But it's
look
worth
into that
thinking
OSDU stuff.
Hmm.
That's a good effort.
Yep. Well, guys, if there's
That's
anything
gonna be-
else,
Yeah, I was going to say perhaps the biggest opposition to making, for example, state websites the data more accessible to more people with just query tools, for example,
Mhm.
is the commercial data vendors who went to a lot of effort and expense to collect that data and then format it and sell it. So that's really your opposition. But I think I think things are already in motion. There are commercial vendors now that allow really a fairly high level of access to what is ostensibly public data with some measure of more ease of use than what you can get off the state website. But you're still, at the end of the day, you're still dealing with the opposition is going to be from the commercial vendors who were there first.
yeah. And there's, you know, after a while, there seems to be, at least to me, a little bit of an aspect of rent seeking in that, where I don't begrudge IHS their business, but they're one organization we work with a lot as part of our assessments, and they are, you know, to their credit, constantly developing new resources, new tools, new things they can charge you for, which is great. As long as those tools are useful and valuable, it's not a problem. But then at some point, their sort of like iron grip on a lot of these well curated data sets, they need to loosen that up, or as we were saying, state surveys, and hopefully the USGS can make more of that kind of data publicly available, free to whoever wants to use it, and IHS and the other vendors can create more value added products and not be so rent seeking. But maybe that's not that may not be a viable solution. I work for the government, so we're not even allowed to think about economics in my group. So it's kind of insane.
Well, and they create a lot of derivative products, right, from that data. So, I mean, that's definitely a niche for them. So,
and I've had some colleagues reach out to me recently wanting access to some of the things like TOPS files that we've developed for some of our assessments. And we can generate derivative products, publish those, serve them out to the public. We're shorthanded. These things are all on the to-do list. And just for example, not to complain, I know everybody's working with a lean staff, but when I started in 2009, there were 160 people in our group, and we just hired 12 new folks in the last year and a half, and that only got us back up into the mid 50s. So there's real limit to what we can do with such a small crew, but we're working on it and we're trying to be responsive. So, and I know everybody is, like, everyone's kind of in the same boat, government,
Always
industry, or
contractors.
academic. Yeah. And then there's contractors and that's great. But a lot of times, like, we'll bring people in and, really try to integrate their skill set into what we're doing. And then the next year our budget drops and we have to discontinue the contract. And now all that, all that capability that we've been relying on for a couple of years goes away. And then we're kind of up a creek. So we're at noon, and I don't want to monopolize the Kirkwood Zoom channel any longer than necessary. But again, I want to thank everybody for participating. Special thanks to our speakers, and keep an eye out for this on the YouTube channel. Please share it with your friends if you think it was worthwhile. And like I said, in the next couple of days, we'll be distributing a list of links to participants that you can share. We may also post it on LinkedIn. That's kind of up to Mike, since he's our social media guru. But anyway, everybody have a great day, and hope to see you if we do this again.